power is going through these gears in the transmission. After we've started the car rolling, we want fast pickup. So we shift into second by sliding the sleeve backward to mesh with this gear on the shaft to the rear wheels. The wheel is now turning at 60 revolutions a minute, and the power flows through these gears. For higher speeds, we let the power go directly to the rear wheels. We shift the sleeve forward so that it meshes with the shaft from the engine. The power travels straight from the engine to the drive shaft.
This gearbox contains clutch gear, lay shaft, main shaft and different gears to achieve requirements of torque and speed. In this type of gearbox, all the gears are always constantly meshed. Now the prime question is that if all the gears are engaged at a time, then how the power flows? And here is the solution. The gears mounted on the lay shaft are fixed on it, but the gears present on the main shaft can rotate freely because of use of the bearings. We have already discussed in the previous video. In sliding mesh gearbox, one gear is slided over the other gear. But here is one important point to remember, that in constant mesh gearbox, the dog clutches can be slided to achieve the power flow. The axial motion of dog clutches can be achieved by providing the splines on the main shaft so that dog clutches can easily connect and disconnect with the gears through which power to be transmitted. Now let us see how the different gears can be achieved. To get the maximum torque and minimum speed, the smallest gear on lay shaft must pass the power to the largest gear on the main shaft. So if I slide dog clutch D2 towards left side, then it will connect with the gear E and power flows through gear A, B, lay shaft, gear F, E, dog clutch D2 to the main shaft. At the second gear, torque speed requirement changes. So meet the requirements, power must be transmitted through gear C to gear D, but this can only possible if we shift the dog clutch D1 towards right side. So in this case, power flows through gear A, B, C, D to dog clutch D1 and the main shaft. At the top speed, power flows directly through gear A, dog clutch D1 and the main shaft, provided that dog clutch D1 must be slid towards left side. And the last case is reverse gear. If we introduce one small gear H between gear G and gear I, then it is possible to rotate the main shaft in opposite direction. But the condition is dog clutch D2 must be slided towards right side and power flows through gear A, B, lay shaft, gear G, H, I, D2 and the main shaft. Okay.
When changing gear, their speeds must be synchronized so that the engagement sleeve can move smoothly into engagement.
Shaft to the counter shaft and are always connected or in mesh. This gear on the drive shaft going to the wheels is free to turn around the shaft. We'll put it in mesh with another gear on the counter shaft. These gears are always in mesh. And keep turning while the engine is running. To switch from one set of gears to another, our transmission needs a short shaft like this, known as a clutch sleeve. It cannot turn on the drive shaft, but it is free to slide back and forth. On the sleeve, we'll mount a large gear, which we can shift back and forth to mesh with the small gear in the middle of the counter shaft. We are now in neutral. The gears that are always in mesh are turning over with the engine, but the shaft to the rear wheels is standing still. A 3,000-pound automobile takes a lot of force to start. So in low speed, we get the greatest leverage by letting the smallest gear on the counter shaft turn the largest gear on the drive shaft. The engine on this model
This section examines gearbox operation. In a rear-wheel drive manual transmission, the splines on the input shaft engage with the splines of the clutch-driven plate. With engine rotation and the clutch engaged, the input shaft transfers its motion through the counter shaft to rotate the gears on the main shaft. In this neutral condition, the engagement sleeves and hubs splined to the output shaft are stationary. No drive is transmitted to the output. Depressing the clutch pedal removes the engine load from the input. This allows an engagement sleeve to be moved into engagement with the external teeth on the gear selected. This locks the gear to the main shaft. When the clutch is released, the drive is transmitted to the input gears along the counter shaft to the gear selected. Since this gear is now locked to the main shaft rotates and transfers the drive to the final drive unit. The speed ratio and the torque transferred depend on which gear is selected. In this 4-speed transmission, first gear, the smallest on the counter shaft, meshes with the largest gear on the main shaft to give first gear. This is the lowest forward ratio. The greatest number of turns of the input are required to achieve 1 turn of the output. This also gives the greatest torque multiplication. In second gear, power flow is through the next adjacent gear. The difference in speed between input and output shafts is reduced. Fewer turns of the input are required to give 1 turn of the output, but there is less torque multiplication. When the engagement sleeve for third gear moves into place, drive is transmitted through the meshing gears at an even higher ratio. In fourth gear, the input and output shafts are locked together. This provides a direct drive with a 1-to-1 ratio, with no reduction through the countershaft gears. The input and output shafts turn at the same speed, and therefore there is no torque multiplication. The countershaft gears and their corresponding gears on the main shaft continue to rotate, as the countershaft is constantly in mesh with the input gear, but they do not transmit any drive.